So a very warm welcome everyone to this seminar. We have today Professor Stefano Liberati from SISSA, Trieste, who will give a talk about causality, time machines, and faster than light travel. We're very much looking forward to your talk, Stefano. Thank you very much for having accepted our invitation today. I'll leave it to you.
Thank you. Thank you for the invitation. It's a pleasure to be here. So today I'm going to make a talk concerning stuff that usually physicists have trouble to speak about because they consider this kind of, arguments that are those things that you know on the background of your mind, but you prefer to not speak about, right? Because they make you look not serious. Well, let's see if I can... So in reality, I think that these kind of issues, time machine and so on, they do deserve attention instead by people working, especially in gravity, because you see, the problem is that we are in a situation in theoretical physics where on the side of gravity, we have a theory that works very well, which is general relativity. On the other side, we know that this theory cannot be the definitive theory of gravity. We know because it's not predictive around singularities. We know because there are tantalizing hints that this theory may have an emergent nature. And we know that it is difficult to reconcile this theory with quantum mechanics. On the other side, we are not completely hopeless in the task of going beyond, exactly because this theory has some cracks. And I like to cite always this verse by Leonard Cohen, which is that from the cracks that light get in. This is Anthem and some songs by Leonard Cohen, which I think is very appropriate. When you are stuck, you need to look for the point of crisis, where the point where the theory doesn't work so well, where it basically shows some kind of problem. And then it's where these problems are that you have to dig, because those might be the way through which, the windows through which you may see how to go forward. And in particular, when we talk about faster than light and time travel solution, this is exactly the kind of case that where these things applies. So let me try to move forward. First of all, let's agree on what we mean by time machine, right? Time machine normally in loose terms is the fact that you may have a region of space-time where you are able to follow trajectory which are allowed by two physical observers, and through this trajectory in space-time, this evolution in space-time, you can come back to the very same point in time and space where you start. Basically, the possibility to have chronological loops. Technically, basically what it means that you have a region where the chronological order is violated. These are chronology violating region. A technical definition is that if you take a point in space-time and look at the chronological future, so basically what happens is that when you have a chronology violating region, you have points in this region as such that the chronological future of a point is the intersection with the chronological past is not a zero set measure. It's something that is not a void, right? And the problem is exactly telling you that if you look at the future evolution from some point, you can enter in the past of that point. And that is basically telling you that there are closed time-like curves. So this is the technical terms. And a region is the collection of this point. And if you have a space-time which is everywhere else same, normally it shows a boundary. A boundary is basically the region is separating the region where there are no closed time-like curves to the region where there are closed time-like curves. And this is what is called a chronological horizon, which technically is the boundary of the chronological future of a chronology violating region. Now, these chronological horizons are basically sheet covered by null rays, but means by light rays, okay? And they normally coincide with causal horizons that separate the causally disconnected region. And they are also a very special case of Cauchy horizon. What is a Cauchy horizon? It's basically a boundary beyond which you cannot do a Cauchy evolution. That means I set the initial data on a slice and I evolve this slice, this data in the future. And there is a boundary through beyond which I cannot basically predict the future of my data. This is basically a breakdown of predictability, which is obvious if you have a closed time-like curves. You don't separate anymore future with past. So why physicists do not like chronological horizon and time machines? Because they generate logical paradoxes. So probably you've already heard about this, but let me just summarize. There are two kinds of paradoxes that are associated to time machines. One is the so-called grandfather paradox, and the other is the bootstrap paradox. The grandfather paradox is very simple to understand. Imagine you go back in time, and by doing so, you arrive in the past, and you want to meet your grandfather, but even without willing, you push him, and he goes under a tram and dies. Before to meet your grandmother, and then before to basically become the father of your father or your mother. And that, of course, is a paradox, because then it's not clear where you're coming from. Another kind of paradox is the so-called bootstrap paradox. This paradox is of a different kind, but is very similar in many ways. So imagine you are passionate for Beethoven music, for example, for the 19th Symphony of Beethoven. You take a time machine, you go back in time to meet Beethoven, and you find that Beethoven is so depressed that he's not writing anything else. And so it's not going to write ever the 9th Symphony. So you get very worried, and you decide that you have brought with you the 9th Symphony because you wanted an autograph, and you basically give it to Beethoven, such a way that Beethoven doesn't write the 9th Symphony, but basically is using what you brought from the future. Then basically there is information created from nothing, and it's not clear at all where this information was created in first place. Of course, a bootstrap paradox can be easily transformed in a grandfather paradox, because in the future you may not decide at the second time to go back in time to bring the 9th Symphony to Beethoven, and then you would create a grandfather paradox. Of course, there are possible solutions, but they're all extreme in a certain sense. One solution is that once a paradox happens, basically you have to accept that timelines bifurcate in a bit like in Borges' garden, and then you have all these parallel lines in which timelines which runs parallel in the same universe. And you have to use basically a mathematical machinery to do physics on this universe, which is completely different from the Riemannian manifold we normally use. The alternative is that there are multiple universes, that this bifurcation really is associated with the fact that there are multiple parallel universes, and basically at each instant of time, your timeline, your consciousness steps from one thing to the other, depending on this kind of decision that, and so if you go back in the past and you kill your grandfather, you still exist, but you exist in a timeline different from the one from where you came from. So that is another radical possibility, and I'm quoting here some movies that use this kind of ideas in the past. Another conjecture is called the Novikov conjecture, and the Novikov conjecture is a kind of I call it a real socialism conjecture, because what it's asking basically is saying, look, if you go back in time and try to change the past, you can't, because it has everything to be consistent. And so you may try, for example, to push your grandfather under the tram, but not only you will not manage, but maybe you will end up doing those actions that indeed happen, so that your grandfather, for example, met your grandmother, and they were always telling that he was saved by air and he was pushed by some crazy guy that was trying to kill him that they never saw again. So you had to go back in the past to do the things that actually happened in the past so that the future was the one you were coming from. So you can imagine that this is a very complicated things to enforce, because one thing is that, for example, there are toy model where you do this on a billiard table with pool balls, and you can make with few balls the system consistent with periodic condition. But imagine that you want to do this to reality, and even more, imagine that you put in the game quantum mechanics. Imagine that what you do in the past depend on what happened to a quantum mechanical experiment. It means that that experiment must give always the same answer in the past for everything to be consistent. So it's not clear how to enforce this. Anyway, this is also was used in some storytelling, as you may know. And then there is what normally, I would say more broadly in the physicist community is considered the most promising route, which is basically saying that there must be a chronology protection. There must be something wrong in generating, taking a completely same space-time and turning it in a space-time where there is a causality violating region. And something must go wrong, especially if you take into account quantum mechanics. That is the basic idea. So we will go back to this issue later on. So you would say, okay, great, but then should I really worry? I mean, first of all, does general relativity allow for time machine if they are so, logically terrible? And the answer is, unfortunately, yes, or fortunately, because this is, you may say, is one of the cracks in the wall that we are looking for in the wall of the perfection, say, of general relativity. General relativity do allow for time machine. That is a definitive statement. Closed time-like curves are allowed in general relativity, and it's not so surprising that they are allowed, because you see, time is a local concept in a general relativity associated to, which is always attached to the experience of some set of observers. And in a certain sense, there is this plasticity to space-time that you have to deal with. And this plasticity can generate conditions for you that allow closed time-like curves. There are basically two classes of solutions that are dangerous in general relativity. The first class is the so-called class of rotating space-time. For example, the Van Stockholm space-time is a dust cylinder which rotates, and where you have a weird distribution of the energy density, which grows with the radius. Then there are GO time machines, which are cosmic strings rotating one another. You have Gödel space-time, which is a kind of cosmic carousel, or the interior or a rotating black hole, like in Kerr solution. There are all dangerous, so we will go back to them in a second. The alternative is that you can create a space-time which is dangerous for causal order by or changing the topology of space-time, like you do in a wormhole, or by allowing basically faster than light travel, which also wormhole does. But you don't need necessarily to change the topology of space-time to do that. For example, there are solutions like warp drives or Krasennikov tubes. So let's analyze a bit more in detail this kind of situation. So two examples. One example is the Gödel universe. So the Gödel universe is a fascinating solution, which was found by Kurt Gödel, the same guy of the incompleteness theorem in mathematics, as a birthday gift to Einstein, which is remarkable. It's not only because it was a birthday gift, but because it was basically a birthday gift that probably Einstein hated with all his fiber, because in a certain sense was done exactly to disprove some of the beliefs of Einstein concerning time in a general relativity. And what is this solution? It's a solution of a universe which is filled with dust and cosmological constant. So you see, also in a certain sense, ironically, this is a universe which has the same content of Einstein universe, the one that Einstein devised in order to have a static universe where the cosmological constant was balancing the dust. And it is a universe which is endowed with rotation. It's a homogeneous universe. So any point, around any point, you can place yourself in any point of this universe. You see an axis of rotation at that point, and you see the universe rotating around you. What is happening is that the light cones, as you move away from the axis of rotation, bend due to this rotation. And when they bend so much that one side of the light cone, hello? I heard some noise. I don't know if it was a question. Anyway, when the light cone touches the closed curve, basically what you have is that you see this is the boundary of the light of this light cone. So light can do a circle, can stand on a circle and a closed curve here. If you go even an epsilon outside of this boundary, what you have is that a ray, which is time-like in nature, that means the ray followed by an object endowed with a mass, can close a circle. So even for us, it would be possible to come back in the same point in space and time. So this universe, of course, is a problematic universe. It's not our universe because we don't see this kind of cosmic carousel. But nonetheless, it was evidence that there is something intrinsically, let's say, non-fixed by general relativity. The fact that it can allow for such solution is quite puzzling. Even worse is when you look at rotating black holes, because now you are talking about a solution that we are pretty much convinced is up there in the sky. Now we have a strong evidence that there are objects whose geometry, at least just above the would-be event horizon, is very well described, the geometry found in 1963 by Roy Kerr, describing rotating black holes. Now, the problem is that if you believe at this metric, at the structure of the geometry below the horizon, you have another horizon, which is called an inner horizon, which is also a Cauchy horizon. So it's one of those horizons that do not allow you to basically evolve a Cauchy problem. But even worse, you have inside the ring singularity, a place where basically the Einstein equations are not predicted. But around this singularity, you have a region where basically it is possible to have closed time-like curves. And this is problematic because this is a solution that we believe it exists. However, there are strong hints that the inner horizon of this curve black hole might be unstable. So normally, the way out by most of the physicists is the following. For solutions like Vostochum rotating cylinders or get a universe, they say, okay, these are GIGO solutions, which is garbage in, garbage out. You have a very weird initial condition, you get out a very weird behavior for your solution. But should we worry about? Well, you see, a theory, it is like a machine. You know, you put some input and it gives you a prediction. If the input is unphysical, the prediction is unphysical. So many people didn't think this solution, they're conceptually interesting, but they're not something we should worry about. What about the Kerr solution? Well, as I told you, many people, the consensus is in the community is that you shouldn't trust the solution below the inner horizon, and all the closed time-like curves are confined below the inner horizon. So, okay, in any case, we shouldn't worry about that. But things are not so simple when you come to faster than light propagation, to shortcuts in space-time. And why this is not so easy to accept? Because you see, these are solutions where basically all you need is exotic matter, basically matter which is violating some condition over energy. So you may say, okay, but this is it's not standard matter. So what will keep, for example, the throat of a wormhole open? Well, the problem is that this energy condition, which are a kind of input you put in the Einstein equation for them to be predicted, are really something that can be violated, for example, from quantum effects. Vacuum polarization violates many energy conditions. Hawking radiation violates all the energy conditions. So when you put quantum effects in the game, it doesn't seem so difficult to violate energy conditions. Of course, to have a 1 meter throat open for a wormhole you need a Jupiter of energy condition violating matter, which is a lot, much more with what we can do in experiment in a lab. But again, this, you may say, is not a physicist problem, it's an engineering problem. Let the engineer work it out to accumulate enough energy. Nonetheless, normally also here people say, okay, but you are calling to cause wormholes, and wormholes, you know, are topologically non-trivial. In order to change the topology, when you try to change the topology of space-time and or opening a wormhole throat, in general, quantum field theory in curved space-time predicts a lot of particle production, actually infinite. You have divergences, you have stuff that is not under control, you may need quantum gravity, and then you wave your hand and you say, okay, whatever. And or you may say, okay, you may have that the level of, if you look at the Planck scale, space-time is a kind of Wheeler foam. It's looking like a foam where there are micro wormholes, and you may be able to basically pump negative energy into them in such a way to make them macroscopic. But again, that implies a manipulation at the level of the Planck scale, so it requires, again, quantum gravity. So normally people, let's say, okay, well, okay, I will worry once we understand quantum gravity. Okay, so you don't like also this one. Another possibility is to have a warp drive. Now, a warp drive, for many of you may remember stuff like Star Trek. And indeed, the name warp drive was given by Alcubierre to a solution he found while he was he's a Mexican physicist doing numerical general relativity that found the solution during his PhD. And given that he was passionate about Star Trek, he basically gave the name warp drive because he's actually doing the same things that the warp drive in Star Trek does. So what is a warp drive? It's a bubble of flat space-time in which you put your spaceship, and then basically you have energy that expand the space-time at the behind the spaceship and contract it in the front of the spaceship. And then you need exotic matter in this region on the side to keep the bubble stable. The problem is, you may say, but okay, wait a second, you cannot travel faster than light. The problem is that in general relativity, the statement is locally the speed of light is not, the speed of object cannot be faster than the speed of light. But nothing forbids in special relativity to have a different region of space-time moving at speed which are larger than the speed of light. Indeed, in our universe, we see a region of the universe that are receding away from us, speeds which are way larger than the speed of light in principle. But it's not that the peculiar velocity of the object of those galaxies is faster than the speed of light. It's really that the space-time itself is expanding in such a way that for us, those regions are receding faster than the speed of light. So it's different. No? It's not violating the fact that locally space-time is flat and dense, special relativity holds. Now, these objects, in principle, are allowing you to travel at arbitrary speed. They are not per se time machine. The problem is that once you have a faster than light propagation, you rapidly gets in trouble. So let me try to make the statement. If you have an object that is able to travel faster than light, but at the same time, you have a special relativity holding locally, what you can do is the following. Imagine you are in a system of reference Tx, and you have you start with your warp drive at instant and in the event epsilon 0, and you propagate faster than light. You see that it's faster than light because light would be traveling at 45 degrees in the Tx system of reference. So instead of traveling at 45 degrees, it travels with a larger speed than the speed of light. This is the warp drive. Then you arrive in epsilon 1. Now, you can choose another system of reference, which is boosted with respect to the first one. And this is represented in this way in the graph. It's x prime t prime. Now, draw a line parallel to x prime, is this dotted line. This is a line of simultaneity in this system of reference, right? So it means that if I travel on this line, in this system of reference, it's like I'm traveling at constant times. I'm traveling with infinite speed. Now, our warp drive doesn't travel with infinite speed, but travels still in any frame with arbitrary speed, with a larger than light speed. So it can go from epsilon1 to event epsilon2. And you see, in this system of reference, it's moving in the future in T prime because it's moving above this dashed line, which is the surface of simultaneity of the X prime T prime. So I get back to the epsilon2, but this is before epsilon1 in the first system of reference. So in that system of reference, I've traveled to the past of epsilon1. Then I just wait and I close the circle and I'm back to epsilon0, sorry. So epsilon2 is in the past of epsilon0, same point in space, but earlier in time t. And then basically I've traveled back in time. So you see, what is the problem here? The problem is that I'm using the Lorentz invariance. I'm using the fact that I can use a special relativity. If you would have instead that you are superluminal only in a given system of reference, then you would see that you always travel forward in time in at least the privileged system of reference. So the comment what it is that it's a lesson that very often is overlooked. It's not that faster than light propagation per se is dangerous. It's faster than light propagation plus Lorentz invariance that create a problem. If you have a faster than light propagation in a preferred system of reference, you don't have causal loops. Now, this is important to understand. Otherwise, let me make an example. In Bose-Einstein condensate, you have that quasi-particle propagated with a superluminal supersonic dispersion relation. And the space-time has a causal structure, the emergent space-time felt by this perturbation on Bose-Einstein condensate is as a causal structure determined by the speed of sound. So in principle, you could have a causal loops in condensed matter, which you don't, because in condensed matter, you have a preferred frame in which you have to do your physics. Okay. So is it possible that you do with the faster than light travel closed time-like curves in general relativity? The answer is, if you use just general relativity, the answer is yes. And it's easy to do this. Here I have example done with wormholes, but you can replace the wormhole with the superluminal warp drive. It works the same. So you can do, for example, a trip, which is a circle closing in time and space, just by using a couple of wormholes. Another possibility is that you take one wormhole with two mouths in the same universe, and one is brought close to, for example, a black hole, so that times is delayed. And then what you can do, well, here actually is the different case. It's the case in which you accelerate you away from one wormhole mouth with respect to the other. So what happens? That the time clicks at a different rate for one mouth with respect to the other. So take, for example, a signal going from tick 1 of the left mouth. It travels outside, so it takes a finite time, and arrives to the second mouth at when the local clock there is at tick 4. Now, once it enters here at tick 4, it has to exit exactly at the same time of the clock on the left, because it's instantaneous, basically coming back. So you exit here at 4, then you travel outside and you arrive just before 8. Here then you exit immediately before 8, and so on. And you see what is happening. There is an accumulation of these rays until you have one final point where you enter at 10 and you exit at 10. This is the chronological horizon, this light-like surface, right? If you take a ray above this horizon, what happens? Imagine here, you enter at 13, you exit from the left mount just before click 13, and here you arrive before you left, because you arrive here, which is click 10.5, so you are supposed to exit here. So you do a trip like this, and then you exit here, and then you have basically a closed time-like curve. So you are in a region where there are time machines. And it's very important that if you have a region which is sane and a region which is insane because there are time machines, there is always an horizon, a chronological horizon. And that is a very important structure where people try to understand, is this chronological horizon, which is also a form of Cauchy horizon, so is a place where you cannot evolve your hyperbolic equation and have predictability. Is this okay? Oops, sorry. Is this okay? Well, the issue is exactly this. If you now take into account quantum mechanics, you see this infinite accumulation of rays here is spells trouble, because it's absolutely telling you that the energy density in this region is growing, and is growing exponentially. So you have an accumulation of energy in proximity of a chronological horizon, and this in general will destabilize the solution, because it will back react on the metric, and then you have to see where you are going to go. The problem is, however, that there is a theorem, I think back to 1997, that is telling you that our theory of quantum field theory in curved spacetime is not predictive when you get on a chronological horizon, basically because you don't know anymore how to renormalize away the infinities that you find in quantum field theory in calculating the energy and the energy density and the pressures associated to the accumulation of matter close to a chronological horizon. So we have the very strong hints that somehow there is going to be an unstable, an instability generated close to a chronological horizon, that the metric cannot remain stationary, that means time independent. We'll have to feel the back reaction. However, we don't know how to compute, and then people say, okay, in order to have the definitive answer, we need quantum gravity. Okay, do we really need quantum gravity? So what I'm going now to discuss is a particular case where you see that even without arriving in a regime where quantum gravity is necessary, there seems to be some kind of uneasiness of space-time toward the faster than light solution. That means it looks like even before to build a time machine, the basic ingredient, which is the possibility to have something that allows you to travel faster than light, is problematic from the point of view of stability of the theory. So let me try to make an explicit example. So, okay, this way is for you, for those passionate about Star Trek. I think it was a due citation. Anyway, let's imagine we want to build a warp drive and try to analyze really mathematically what did you see. This is what you see, even if you're not working general relativity. This is basically an equation telling you the structure of space-time for describing a warp drive like the one represented here. Now, a very important point is that what you can do is that you can say, okay, let me say I start with flat space-time, and then I want to generate dynamically this bubble, which start moving at speed faster and faster until it's superluminal. We all know already that you need for this solution exotic matter on the side. But basically, what is the first observation that you need to do? That as you take this bubble, this region of space-time, and you make it accelerate until it becomes of constant speed and superluminal speed, what is happening is that place yourself in a spaceship inside the bubble. If you look at the back wall of the bubble is moving in this direction, toward the left. So what is happening? If you look at the back, no signal from outside the bubble can reach you, because they have to travel locally faster than light in order to cross this the boundary of the back wall of the bubble. So from you, this back wall is basically like a black hole horizon. Nothing can enter in your portion of space-time, the interior of the bubble, from outside. While this front wall of the bubble is exactly the contrary. Given that it's pushing forward faster than light, stuff can enter this direction, but nothing can escape from inside the bubble toward the exterior from the front wall, because again, here inside is flat space-time. The speed of the signal is the speed of light. This front wall recedes away in front of them faster than light, so they cannot basically cross it from inside. Only stuff can access from inside. So this is the time reversal of the black hole horizon, which in jargon is called a white horizon. Now, what is happening is that if you perform, and this is a way to graphically represent this as a region of flat space-time, which evolves to horizon, the back wall of the bubble, the front wall of the bubble, and this is the region inside the bubble. And what you can do is that you can quantize a massless scalar field. We did it in one time dimension and one spatial dimension for simplicity. And what you get is that you can get the expression for the energy density of the scalar field developed in this region at light time. And what you find is that there is a static contribution that doesn't depend from the way you produce basically the superluminal warp drive. There is a dynamical contribution corresponding to a flux in this direction, right going. And then there is another contribution which is left going in this direction. This left going contribution basically is due to the acceleration in the transient phase and fades away at late times. And so what they are important is the static contribution and the dynamical contribution in the right going direction. So what do we get? If you look at the energy inside the bubble, at the center of the bubble, you find that the static contribution vanishes. And the dynamical one gives you a thermal bath at a fixed temperature, which has basically the same formula of the Hawking temperature responsible for the evaporation of the black hole, which is not so surprising. Basically, what you see is you have a thermal radiation coming from the back wall of your bubble because it looks like you are, behaves like the event horizon of a black hole. And basically, you have a thermal bath at this surface gravity, which is determined basically by the sharpness of the walls of the warp drive. The thinner they are, the larger this K, this kappa is, and so the higher, the hotter is the thermal bath you experience at the center of the bubble. If you look instead at the energy at the boundary of the bubble, that means at the two horizons, the back wall and the front wall, you have that there are two diverging contributions there. The static and the dynamical contribution diverge, but they cancel out exactly. And you have a residual term, which in the case of the black wall is exponentially suppressed, so give you basically zero. In the case of the front wall, there is a plus here instead of a minus, and so you have something that grows exponentially with time. So what is this? This is basically telling you that there is radiation coming from the back wall of the bubble, and it's basically accumulating on the front wall. So you have exponential increasing energy at the front wall. And this, of course, it means that your bubble is going to be destabilized. It's going to explode, basically, you would expect. So there is, what is the upshot? That if you try to do a superluminal warp drive, which is the initial ingredient to do a time machine, in general, they are unstable by quantum mechanics. Not only, but given that if you don't want to have a lot of exotic matter, you needed to do the wall of the bubble very thin. So the temperature I was talking to you about is going to be very hot. So you're going to be boiled in the center of the bubble. But imagine you have a very well, isolated spaceship, but still your bubble will be destabilized by this accumulation of energy at the front wall. So it seems that quantum general relativity plus quantum field theory basically know that faster than light is dangerous. And even before you have a chronological horizon, you try to use this to build a time machine, you are in trouble having a stable object which is moving faster than light. And note at this point that even if you are 99.9999% of the speed of light, so even if you are even slightly subluminal, those back and front wall are not acting as horizon, and you will not have this generically this instability. So it's really the superluminality that spells trouble for the stability. This was looking for a long time as the end, basically a nail in the coffin of warp drive, a superluminal warp drive. Subluminal one are still fine, so there is still hope for Star Trek. However, this year it came out a paper which was a kind of follow-up, try to go in higher spatial dimension to have a more realistic calculation. So we live in 3+1 dimension if you're not a string theorist. So if we live in 3+1 dimension, in principle, you should do the calculation in 3 spatial dimension and 1 time dimension. And what they found is interesting because they found that our result still stands, but it is present only in some points of the front wall of the bubble, not all over the front wall. And that implies that you have points where energy is accumulating very efficiently. So what you can do, you can try to shape the bubble in such a way that the surface gravity at this factor kappa that you see here, this little kappa that you see here, which is basically the surface gravity, the local acceleration you need to have in order to stand still at this horizon, this kappa, if you make it almost zero, then you can have a long-living superluminal warp drive. Another possibility is that instead of going straight in one dimension, you zigzag, so you don't allow the energy density to accumulate. However, there is an open question. Can you build a time machine if you are superluminal for finite amount of time and with this very particular surface gravity at the walls of the warp drive? Is far from clear, and my guess is that the answer is no, but that is something interesting to look in the future. So I would say that in spite of this recent result, it's still telling you that somehow quantum gravity will try to avoid time machine and faster than light travel. So I just want in the last part of my talk to give you a toy model of how this may happen. And this toy model is based on intuition, which is coming from a possible toy model of emergent space-time. So emergent space-time is the idea, the emergent space-time idea is basically the idea that we do not have to consider gravitons as, the quanta of space-time, and in a certain sense, the general relativity is not on the same foot of a fundamental theory or like the standard, electromagnetism. The idea is that somehow space-time is an emergent concept. It's like of the hydrodynamic limit of a more fundamental theory, which has other variables, and that in a certain sense, the metric is a collective variable. The graviton is like of a collective excitation. And in a certain sense, this is what happens in most of models of quantum gravities nowadays. There are very few models where basically the discreteness is not fundamental. It's kind of a cutoff to make a calculation, and that you pull it away. Like, I don't know, the analog would be what we do in lattice QCD. There are some models in this sense, but they're not what most people see nowadays. Nowadays, the discreteness of at a small scale is fundamental, is a feature, and you are not characterizing what is space-time at small scale by quanta of the metric, right? You have other structure, and then generally you have operator, you take the expectation value on coherent states of this operator, of this quantum operator, and then you have a classical limit that you call space-time. A system motivated from condensed matter are basically doing the same. And there is a whole branch of research, which is the so-called analog gravity. So let me give you an example. In analog gravity, the typical example is that you have a continuity in the Euler equation for a fluid with some viscosity. And if you take an irrotational flow, that means basically where the velocity can be written as the gradient of a potential, of a scalar, and you have a barotropic equation of state, and you have a viscosity 0, it's viscosity free. Basically, if you have a perfect fluid and look at perturbation, you get a set of linearized equations, and you can basically, from two linearized first order equation, you get a second order equation by eliminating one of the variables. And then you see that, for example, the scalar degrees of freedom, which is the perturbation in the velocity potential, propagates like a scalar field and a curved space-time described by this metric. And this metric is sufficiently general to describe many physically interesting solutions, for example, black hole, cosmology, and so on. And this analysis can be generalized to relativistic fluid. So, of course, emergent gravity, normally there is an argument that there is a theorem by Weber-Witten that forbids it. But this theorem basically is assuming a lot of stuff, and in particular Lorentz invariant. And there are way to bypass this. One is simply that you have a one-step emergence. You have the structure with space-time atoms, and then they condensate and they form at one go basically a structure like the one we observe in everyday life. So you have a Riemannian manifold with a metric, local Lorentz invariance, background independence, and locality. Or you may have an emergence where the space-time atoms basically produce a differential manifold with a flat metric, no gravity, fields with a form of locality, which doesn't have to agree with the locality that we see in our life. And then you have a second step where from this you can combine fields in such a way that they generate a system which has all the local Lorentz invariant background independence, at least at low energy that we observe. Condensed matter model are providing exactly an example of this sense. And what I want to do here is basically show you a toy model where let's assume that you have some discrete object that in some large n limit produce a differentiable manifold, which has a Euclidean metric, has no time. It's just space. And we assume for simplicity that this metric is also flat. And then we have a collection of scalar fields that are propagating on this metric. Propagating is not the right term, but that have some equation describing them on this metric. Now, we don't assume for simplicity any direct interaction between the scalar field, no external potential, but we assume that they may have a kinetic term of what it would be, or let's say Euclidean kinetic term, which is totally general, is not the standard one. I want to show you that you can emerge time in this situation. So let me just take it. You have some Lagrangian with n fields, and here you have, these are the fields psi, and these are what normally would be called the kinetic term, but here instead of having a metric, you have basically a Euclidean delta. And then we also assume that basically there are no couplings, so the kinetic term, you adjust that this Lagrangian is the sum of the Lagrangian with each kinetic term. You do this equation of motion, and what you can do now, you say, okay, these are the equation of motion. Now I want to consider a solution of this equation of motion plus a perturbation, very similar to what people does, for example, in Bose-Einstein condensate. And then you will have the kinetic term for a given field plus the perturbation, and this is the structure of them. And then you consider basically an expansion of this Lagrangian. What you can do is that you can show that you may ask yourself, okay, in this expression, this term basically is this first term this is the Lagrangian for the background field. This term is zero because if you enforce the equation of motion, because you see this has to be basically constant. And then you have this term, the second order term. And you may want to ask, is it possible that the perturbation field instead a Lorentzian geometry, which has time? Is it possible that basically their equation of motion can be written in this way? And the answer is yes, you can do that by basically looking at what is the effective geometric that appear in their kinetic term. And you see, the fact is that you have this non-trivial term coming from the fact that we haven't assumed standard kinetic term for the initial fields. And then you can ask, can I have that all the perturbation seems the same metric and that this metric has a Lorentzian signature, has a time instead of having three spatial directions? And it's also flat, that means flat space-time. And the answer is that if you enforce that all the f of k are the same, all the fields are the same, and in addition, you ask that the background solution has this form, basically is a function of it's a simple function of the coordinate that you can further simplify, assuming that there is no preferred spatial direction in the initial system. Then you can show that you can have basically propagation on an effective geometry for the perturbation, which is a Lorentzian geometry. So it has a notion of time in the sense that it has a dimension which you can go only in one direction. There is a one-way direction with respect to the other one, which are both ways direction. And you can see that there is an explicit form of the initial Lagrangian that would be this, with this value of alpha here, that satisfy all these constraints. So what we have done, we have started with the Euclidean spacetime with a set of scalar fields and non-quadratic Euclidean kinetic terms. And then we have shown that you can select the expansion of perturbation around the peculiar solution of the initial system, such that the perturbation feel a flat Minkowski spacetime characterized by a notion of time, in the sense by a Lorentzian signature or pseudo-Riemannian, as you prefer. So, of course, this is all emergent. If you go to the next order in that expansion I showed you before, nothing of this will be holding. So these are kind of symmetry which are emergent at low energy. So of course, you have no way to pick up the ground solution among another. But of course, in the Einstein condensate, normally this would be associated in which background you emerge to the initial condition of the macrophysics leading to the emergence of our Euclidean system. In a certain sense, here is similar to picking up a ground state for the fields, the emergent Lagrange. That could be, the analogy would be, I don't know, take carbon atoms. They can, depending on the initial condition with which they form structure, they can create diamond, which doesn't have a preferred foliation, with respect to graphite, which instead has a preferred layering. So this is something that quantum gravity should tell you. But let me go beyond that. Let's take the same system we just found. We found that under given condition, these perturbations that are scalar field will propagate on a Minkowski spacetime. But there is a symmetry among the scalar fields, which is a kind of ON symmetry. So what you can do, you can emerge this symmetry by saying, okay, I pull out the common amplitude, which is dimensionless, and then I have all these fields, which are constrained to be basically the norm of this vector, phi square, should be a fixed constant which has the dimension of a length square. So you can see that if you do this transformation, this different representation of the field, you get for your Lagrange a structure like this, which leads you to some equation that are like a nonlinear sigma model plus an equation for the field on a given spacetime, and with this constraint for the norm of the field. And you know what is surprising? That you can recast this as the equation where you have a form of gravity where all the metric are conformally flat. That means there is a function of the coordinate times flat spacetime, and where the scalar field propagates on this metric G mu nu. And this theory of gravity is a theory of gravity that we know because we can describe the scalar curvature associated to this metric as a function of this overall capital phi scalar field. And you can rewrite the equation determining the dynamics of the capital phi as Ricci scalar equals proportional to the trace of the stress energy tensor of the little phi field. And this is a theory we know, it's called Nostrum gravity, and is a theory that is a progenitor of general relativity. You see, it's like taking the trace, it's like taking the trace of the Einstein equation. It is, this symbol is saying that all the metric have to be conformally flat, so there is a tensor that you can build, which is called the Weil tensor, which is 0, and it's telling you that all the solution of this geometry are metrics which are a factor times the flat metric. So they have the causal structure of the flat metric, but they can be curved. And this theory was basically an intermediate step to get to general relativity. So it's quite surprising. We started with a completely abstract system in Euclidean geometry. Look at the perturbation. Not only they can propagate like in a Lorentzian geometry, so there is an emergence of time, but not only. The dynamical equation that determining the geometry, they resemble very closely the geometry, the equation for special relativity, for general relativity. So in summary, this is what I just say, and I just want to stress that this is all true at a given order. If you go at the third order, you break down both Lorentz invariance and the background independence. So is it possible that we can emerge space-time in this way and general relativity in this way? And if we're able to do so, is it possible that this kind of emergence basically force the fact that space-time has to be globally parabolic? That means cannot have time machine. Because you see, if, for example, the geometry are conformally flat, if you don't have a kind of singularity in the conformal factor, you expect the causal structure to be the one of Minkowski. So that should be healthy. So conclusion. Okay, it seems that quantum effects not only abort time machine, but even faster than light travel, which is basically the dragon egg that you need to cook an egg omelette. So it looks like there is a preemptive chronology protection, in spite of the fact that maybe you can get around and get metastable superluminal warp drive in a higher dimension than 2. But there is out, we should look if it's possible still to do a time machine. And it looks like if this is true, then the answer seems to be strongly hinting to the fact that once we will understand quantum gravity substantially, as I was telling an instant ago, should be such that is preventing the possibility to build this space-time. We will see once we will understand the way space-time emerges at grand scale, that if you look at the underlying structure, this underlying structure cannot be deformed in such a way to give you, to take operator, take expectation value and coherent state and get a structure that allow for faster than light travel and basically time machine. So I close with this. It looks like we are still there. We still need quantum gravity, but you see, my final point is that this seems to be hinting at the way quantum gravity should be in order to avoid causal paradoxes. And if we will not do that, then we will have to rewrite physics in the emergent world, because we will have to basically deal with them, with bifurcating histories or allowing basically for multi-universe and so on. And we will see what the end will be. Thank you.
Well, thank you very much, Stefano. It was an amazing talk. I will now open the session. So are there questions, remarks? So hold your hands raise your hands in the chat so that I can see them. No questions. No, okay. Lorenzo Maccone.
Hi, can you hear me?
Yes.
Yes.
Great. So very nice. I agree with most of what you said, but I kind of got lost towards the end when you were emerging time. So I'm sorry, I'm not so expert, so I kind of lost track. But what is the Lagrangian you were? I mean, I can't see what a Lagrangian is if you don't have time, if you just have space. What?
Yeah, well, maybe you find appropriate the term Lagrangian. What I mean is that
Yes.
you can have, Euclidean, elliptic equation, right? You can have system. We have in physics system where you don't have time and where you have elliptic equation. So basically, what I'm saying is the following. Imagine that you have a system.
But these are not dynamical equations, of course.
Yes, they are not. They are not. This is exactly the point, because you have only space here.
Exactly.
So,
yeah.
but they are
that's
not
what
empty.
I was missing. Okay.
Yeah, you see, but the point is that they are not empty equation. They are not equation that cannot be seen in some part of physics. They are not dynamical, but the point of which is interesting is the following. You don't need to put time here. You don't need to have a Lorentzian signature for this metric here to get a Lorentzian signature for the perturbation. In analog gravity, what sees space-time, the analog of the matter probing the space-time, is the perturbation. It's like in this analogy here, you have that the background flow of the fluid provides your metric structure. You see, these are all background quantity, the background density, the background velocity. What fills the space-time, what probes the fact that there is a space-time which is not flat, is this psi1. What is psi1? Is the perturbation in the velocity potential. That means in the scalar, whose gradient is exactly the velocity of the fluid. And this is always true. And a rotational fluid is such that the velocity can be written as the gradient of a scalar. So the idea what it is, you don't need to start at the fundamental level with a system which has time. And here time is really a primitive concept. There's nothing to do with the second law of thermodynamics. Really having a a direction, a dimension that is not on the same foot of the spatial one. A dimension that is one way, is a free way, which is one way, is not two ways. In space, we can move outward, inward, left and right, and there is democracy between the two directions. In time, we can always have them.
I don't know what you mean by moving in space if you don't have time, right? Because you can't move. So I'm not sure.
I'm talking about now the dynamic of the perturbation. I'm talking phi fields.
Okay.
We have just seen that the phi fields have an equation, which is the equation for, let me see, it's here. At the end, you get that basically you have a kinetic term, which is, it's like to have a D'Alembertian for the phi fields in a space-time, which has a metric, which has a time component, which is negative. So it's really a Lorentzian signature. And then it has plus, plus, plus on the other component. So this is an equation where you do have dynamics. You have the possibility to evolve and you can move in space in this other 3 dimension back and forth. While in this dimension, given that you give a different sign exactly because you want to say that in that dimension you have only one way. There is a one-way street. You cannot move backward. So you have isotropy space, but not in time. And so the example is just a toy model to show you that even if you have a world where there are fields on a timeless space, still the perturbation associated around the solution of this equation, you still can mathematically speak about solution with a Euclidean signature. It's not that you have an elliptic equation, you find a solution. And
it's
perturbation
not
around this solution, it doesn't matter, it's still the solution of the elliptic equation. Okay. And then you can expand around this solution and you see that the perturbation instead can see. And then if we are made of matter, we may be in the situation of this phi field and identify that there is a time that, but just because we are perturbation on a timeless system.
Yeah, that's fascinating. But is it an additional degree of freedom that comes out, or is it there from the start?
Which is the degrees of freedom, little phi?
This time, did you start from a 4-dimensional Euclidean manifold, or you started from a 3-dimensional?
It was everything. It was in 4-dimension, 4-dimensional Euclidean manifold. Okay. We didn't change the number of dimensions.
And one of the dimension becomes time.
And one of the dimension for the perturbation is becoming time. Yes.
Yeah.
And instead of 4 spatial dimensions, you get 1 time dimension and 3 spatial dimensions. And this is a trick that you can do because the initial Lagrangian for the timeless system that has this non-trivial kinetic term, because all the point is coming from the fact that you have this kind of derivatives to take into account, because if you would have only this first term, it would be nothing. But still, you see, in a certain sense, it's just a toy model to show you how, even starting from a Euclidean, and you know, in physics, this is something that is not completely alien. In the 80s, there was this idea of Euclidean quantum gravity, and there was the idea that the universe may start in a Euclidean system with a Euclidean signature, and then there is a transition to a Lorentzian signature, and then it starts evolving. Before it's timeless, and then it starts evolving, and that was at some point a very well considered theory for the start of the universe. Again, I'm not saying that, of course, we live. This is a very simple system. It's just a kind of it's this kind of toy models that are teaching you that in principle nothing forbids even to have the emergence of the Lorentzian signature from a timeless system.
Yes. I understand. It's very fascinating. Thank you very much.
Thank you.
Okay, so are there other questions, remarks? You can raise your hands in the chat. Well, then I have some, to be honest, many. So start, so maybe that this generates debate. Please, Marco Forgione, do you want to go first?
Yes. Can you see me? Can you hear me?
Yes.
Sorry, I couldn't find the raise hand button. Sorry.
Okay, so then you go first, and then I.
Okay, so I do have like 2 questions actually. Thank you very much for the talk. It was very interesting. And first of all, I did not fully understand how you pick the background quantities in the hydrodynamic model. Could you say more about that?
In general, in any hydrodynamic model, or in this particular model, toy model I was doing. This was done basically to get what we wanted to get, in the sense that, in fact, there is a comment about this. You see, here what we are saying is that if you wanted to have that all the fields fill the same metric, you need to have the same form of the kinetic field, and that basically they're all behaving the same. And then the background solution will show that if you take a particular background solution, which is a function, and what is called an affine function of the coordinates. So it means you take one coordinate and you say it's proportional to that coordinate plus a constant. Then you can show that you have a unique metric for all of them. And in addition, you want to enforce that this unique metric is Minkowski, and that is done using a form of the kinetic term. That X is the standard kinetic term. So you're saying, and again, it's Euclidean kinetic term. So it's an improper language, but it's the most effective to convey the structure of the term. So if you take this particular example, you can do the job to show that these components are a constant. Basically, what you want, they must have this sign, and they must be constant. And then you are sure that you can basically rescale your coordinates in such a way to write it as -1, 1, 1, 1, which is Minkowski. So
okay, so you choose them based on the getting the Minkowski. Okay.
And I think there is operation. How is selected the background solution? There is no preferred ground state, because it's a Euclidean theory, so you don't have even an ocean of energy. Like an energy is what is conserved as the translation, right? Here you don't have an ocean of energy and hence of what is the lowest energy state. But it's just showing you that if you come up with this kind of background solution, then you can do this. And what I was saying is that if you look at the analogy in a condensed matter system like Bose-Einstein condensate, where you can do basically the same, then basically what you're asking is the background solution is determined by the condition under which you get the condensation. And this is why I say, imagine carbon atoms. Carbon atoms, they can end up in a structure like diamond, or they can end up in a structure like graphite, right? And they're very different in the ordering. Here, there is no special, there is no preferred foliation. Here, there is a preferred foliation. There are the graphene layers, right? What determines to come up with diamond or graphite? The condition under which you basically condensate your carbon atom, which is normally the pressure, for example, right? And that is the point I'm making, that it may be, the idea is that the Euclidean system I started with is already a first step of emergence. It's not the fundamental system. It's coming from atoms. So the Euclidean system can come up with a background solution, which is like the diamond, or it can come up with a background solution like the graphite. And then the perturbation will feel if there is some direct, in some direction, you have something different from the other one. And then you can have basically this emergence of time. I hope I was more clear now.
So I kind of have like a follow-up on that, but I can let people talk first. Okay. So this is a different approach than, for example, Landau's approach in terms of hydrodynamics and the one developed by Bolovic, right? Or is it like the
I don't know what you have exactly in mind by Landau approach. What do you mean by?
A form of basically normalization for starting from an economic approach where basically I'm not expert on that, obviously, but you approximate the basic fundamental quantities to get different possible phases in a sense of like the diamond versus graphite example that you were giving there. But here, like, so your background is hydrodynamic equations, not something like more fundamental entities like GFT or low quantum gravity.
No, because those would be the extra. There are 3 layers in this toy model. There is a layer I didn't describe, which is the emergence from some quantum gravity theory. What I'm trying to say is that even if you take a theory which has no time, the problem is that many quantum gravity theory have embedded time because they are a form of canonical quantization of general relativity. So at the end of the day, maybe they resorted to concepts which are no more gravitons directly, but still they are coming with a time built in. So in those theories, there is already time built in. But imagine you have a fundamental theory of quantum gravity that a priori has no time, right? It's like you can imagine group field theory, right? And then you have an emergence. You don't need to emerge directly space-time. You can even emerge a set of fields on a timeless Euclidean manifold. And still, you may have that if the matter we call the matter of the standard model is coming as perturbation of these fundamental fields, then this perturbation can fill a Lorentzian space-time like the one we experience, even if at the fundamental level, at the intermediate level, it's not the real fundamental. And the continuous limit, you see, you have quantum and discrete. You may have quantum and continuous, and then you have classical and continuous. And then quantum and continuous could be this intermediate level where you have basically Euclidean space, no time, and yet the perturbation of these fundamental fields would be able to see a time, could be see the time if you are perturbing around the particular background solution of the elliptic equation in the Euclidean signal.
So the matter level, so the standard model matter level, so the meso level will still be timeless in a sense.
No,
and still
no, because
from a perturbation. Or no?
No, because the standard model will be this phi field, this little phi field. See what I mean? Actually, it's even worse. You see, in my model, this phi field is not yet the standard model. This phi field fills a Lorentzian signature because we are expanding around, we are picking up a particular class of Lagrange and we are expanding around a particular background solution. But in the toy model, you find out that given that there is a kind of symmetry of this effective Lagrangian, which fills now a flat Minkowski geometry, so it has a notion of time, you can basically separate these fundamental degrees of freedom in an amplitude and degrees of freedom which are basically constrained in this way in order to have a norm which is fixed by some fundamental landscape. And then you see, you end up that the capital phi is a gravitational degrees of freedom, is the scalar factor in Ostrom gravity, which is a scalar theory of gravity, is a progenitor of general relativity. And this little phi is the standard model field. Because now the standard model field propagates on this geometry, which is potentially curved because there is this conformal factor. And this conformal factor is exactly something that Gauss dynamics can be recast in a way which is very similar to the Einstein field equation. Curvature equal content of matter and energy. So the toy model, even if it's really a trivial toy model in many ways, and for sure unrealistic, I find it that is surprisingly capable to go that far in advance, because it's not just telling you that you can emerge for your perturbation time, but it tells you that your perturbation are in principle endowed with sufficient degrees of freedom that they can behave like matter plus gravity, and gravity as an equation which is basically the closest you can get to Einstein field equation, where you have only a scalar degrees of freedom. A graviton has at least 2 degrees of freedom, the 2 polarization. So it's doing, for being such a trivial toy model, a remarkable job. And I think it's just a case study, just showing you that there is much to understand about emergence. And to me, the problem with time machine and emergence are intrinsically related, because you see, if you find out that the way you get from the fundamental atoms of space-time to standard model and dynamical space-time is such that the solutions are forced to be of a given form. And here, for example, they are forced by the fundamental system to be conformal invariant, which is a very strong constraint, which also exclude them, because we know that the metric that we see are not conformal invariant, because otherwise photons would not be deflected by gravity. Eddington saw the deflection of light by the gravitational field of the sun. So I'm not saying that this is a realistic model, but what I'm trying to say is that, you see, it's showing you that if quantum gravity selects the emergent space-time solution in such a way that they are always globally parabolic, they are always times space, then it's obvious that you will never be able to create a time machine, because once you do that, you are basically trying to deform your solution in something which is not a solution of quantum gravity, that quantum gravity will allow.
No, that really helped understanding, especially the last part. Thank you.
Sorry if I wasn't clear.
No, that's good.
Thank you. Are there other questions? Okay, so I have 2 points. So the first one is very easy. So it seems to me that you make a distinction between a sort of one level or direct emergence and a second level or indirect emergence of space-time, correct? There is a slide where you show that the first case is something, well, more than a Nobel Prize if made, whereas the second one is more realistic, let's say. So my first question is, so all solutions implying geometric genesis, you would classify them in your second, let's say, your second class of emergence?
Actually, I don't know if I would put it in the second class.
Yeah, exactly. This is my curiosity.
group field theory, when the only example I come to my mind is group field theory. When you have the analog of the Big Bang as geometrogenesis, if you think about it, they start with group field theory and they get basically the Friedmann equation plus possible modification. But what they get is a continuous spacetime, classical spacetime, which has already local Lorentz invariant. Given that they have a Friedmann equation, apparently they also have background independence and everything in one go. So it looks to me like a group field theory, for example, would go more in the first category. This is the category where models, that are more inspired by analog gravity could work. And there is an interesting paper by Marolf that I cited, but probably didn't have the time to stress, that show that if you want this kind of emergence, there is a point that here the notion of locality, whatever it is for this intermediate step, cannot be the same as the notion of locality here.
Yes.
Which is quite interesting, because it's telling you that, and this is related basically to the fact that you want diffeomorphism invariance. So if you want to have a theory which is truly background independent, then somehow this notion of locality, and in a slight sense, it's not so surprising, because you may have that basically the fundamental system has a notion of locality which is completely different. In a slight sense, atoms in a Bose-Einstein condensate have a notion of what is local based on the speed of light. Quasi-particle phonons living on the Bose-Einstein condensate, experiencing this emergent geometry, have a notion of locality based on the speed of sound. So what is local for the fundamental system is non-local for the emergent system. Exactly. And that, if you think, may have even some consequence. Maybe that when we see in quantum mechanics, this correlation at space-like distances, maybe this is puzzling or is difficult to reconcile with the notion of causality in our emergent space-time. But it's not obvious that the notion of what is local is the same at the fundamental level. And maybe quantum mechanics works at the fundamental level. We see just the shadow of it in the emergent system. So I realize that I'm posing more questions than giving an answer, because that definitely there is not an answer.
No, well, it's no. You clarified the point, because I agree with you that in the case of geometrogenesis, especially in group field theory, you have something more radical You even have the problem of conceptualizing an atemporal transition, but when talking about gematogenesis, apparently authors like Oriti and others, I mean, they mean physical phase transition, therefore, or at least they aim to physical phase transition. Therefore, you would have, conceptually speaking, an achronic transition. And it's very hard, even for philosophers, you know, to think of an atemporal transition. Of course, if you say, well, but you have first to drop the classical notion of transition, the classical notion of locality, so you have, in a sense, to you don't have to define atemporality as the absence, no locality as the absence of locality, but in terms of a different type of it. And you have to do the same for atemporality. So at least this is what we do as a group, as Proteus. But the idea is that, I mean, the case of gematogenesis poses more issues in a sense. Conceptually, especially conceptually speaking. For the second type or the second class of emergence that you describe, I think that you're fully coherent, and I also agree with you that it's necessary to develop a notion of locality that is simply different from the one that we find in relativity. So that's the second question that I have.
Oh, well, let me say, there is enough locality. It must be different if you want the exact different variance. Background independence.
You want the different.
But maybe, you see, the model I was saying is broken at high energy different variance. So it may be that if it is broken at sufficiently high energy, we don't see it. It depends on the scale. I know if you look at this, I mean, it doesn't have a symmetry to be exact, to be physically relevant. It could be just a low energy symmetry, but sufficiently exact at energy that we can probe. So that I realize there are constraints, for example, local Lorentz invariances, you know, which are very, very strong. So it's not easy to get a theory which satisfies all the constraints that we have now from observation. But you see, concerning the point you were making, to me, this second part has the advantage that here you don't need to have an achronal phase transition from no time to time. Here you can go from no time to no time, and simply you have, however, that you emerge a system which has a particular Euclidean structure, particular Euclidean Lagrangian, and a particular background, the solution, like the graphite instead of the diamond. And then the perturbation will see this effective dynamic, but it's a low energy effect.
That's
here is not perfect.
No, that's clear to me, and it's coherent with. I mean, you have shown it very clearly with the toy model, I think. I have another question which regards time travels, in the sense that I've always been skeptical, contrary to many of my colleagues in the field. I've never bought it, let's say, or at least I bought it with the caveat that you mentioned in your talk. So I have a question with regard to, this is just a curiosity. I'll never work on this probably, but let's say, in my experience as an historian of physics, an historian of science, a philosopher of physics, and so on, there is something that attracts my attention in a negative way when I hear the concept of negative energy. Or at least I'm a bit, oh, negative energy. In the sense that, especially in the case of a wormhole, for example, there are some, let's take the example of the bubble, no? That there was one of your slides with the, the capsule traveling within the bubble, where you have exotic matter, right? that surrounds it or whatever. Yeah, exactly. This is the okay. So let's put aside negative energy and exotic matter, exotic components. Let's say that could play some role within this picture. I was wondering, and I don't recall whether you mentioned this, what about pressure and density of this bubble, within this bubble?
Well, when we say negative energy, what we are saying is exactly, if you can imagine you modelize the stress energy tensor, which is basically the right-hand side of the Einstein field equation with a perfect fluid. Then the perfect fluid is characterized by an energy density and the pressure. When we say negative energy, first of all, a disclaimer: we live with exotic matter. Dark energy is exotic matter. What is now pushing the universe to an accelerated expansion is such that is violating a crucial energy condition, which is called the strong energy condition. The density plus t times the pressure in the universe now, in this moment, is less than zero. It should be more than zero for standard matter. So we know that the energy conditions are violated.
Let's put it in this way. When I hear negative energy, or if you prefer dark energy discourses, it's not that I don't think that it doesn't correspond to anything. I'm just saying that we must be careful, because on the one hand, it's interesting because it means that there is more to be discovered. On the other hand, we know so little. We don't know, or at least this is what I know. Maybe that you cannot, you don't confirm this, and you surprise me. But we don't know anything about the origin of dark energy. So we only know in our standard model, in the lambda CDM model, that there is dark energy. It constitutes 68% of the energy density of this universe, correct?
Yeah, but when you say lambda CDM, you already said what is the source of this dark energy is lambda. The cosmological constant, when you write the stress energy tensor, behaves like a perfect fluid in which P, the pressure, is minus the energy density. And so rho plus 3T is less than 0. So a cosmological constant would do that. The energy of the vacuum would do that. In a Casimir effect, if you take two parallel plates, they tend to stick together. Why? Because there is a negative energy density, so there is negative energy between them, and the force tends to.
Yeah.
And in nanomechanics nowadays, you have to take that into account. It's really industrial technology by now.
Yeah, yeah, so, and I recognize this, but then my question is, considering this bubble of your slide, then what do we know about rho within this bubble, and what about the pressure? Because I mean, I can have negative energy in the surrounding. I don't know whether you think that within the bubble there is negative energy.
No, you don't need. Okay, so the background solution of general relativity requires negative energy here on this side. Here is flat space-time, and so basically it's Minkowski, so it's vacuum. There is zero energy density, zero pressure. Now, when you go beyond, and you find basically you quantize a field which would be in the ground state, in the vacuum, and then you take into account what happens to this ground, to this field once it is quantized, then you find a contribution which is telling you that the density at the center of the bubble is like a thermal bath at a given temperature, and instead there is this going to zero energy density at the back bubble, and diverging at the front bubble. So the answer to the question is that when you have a superluminal warp drive and you take into account the quantization of matter fields, then this quantization predicts a thermal bath. Basically, the Hawking temperature is the same formula of the Hawking temperature. It's really, for this reason, it's because the back wall is look like an event horizon, or a black hole event horizon for the spaceship inside. So you know already the answer. We computed it, and but basically, when I realized that we knew already the answer to the question, it was just to prove it with a calculation. My former supervisor, Denisham, always say that you have to do the calculation once you know the answer.
But so you wouldn't say that this is something depending on the mathematics of the theory that we use. It's something that
I think that this is really showing you that, you see, the problem what it is the problem is that when you have the superluminal structure, here is very simple. No, you see really that the causality of space-time is cut. You have basically these surfaces that you can are one-way surfaces. Quantum field theory doesn't like them. In one case, when you are behaving like a black hole, it radiates. It's like there is a friction, and this generates heat going in this direction and filling the interior of the bubble. But in this other direction, there is a problem that nothing can escape from within a bubble. So you have this radiation accumulating on the front wall and then growing, and then back reacting. And I think, okay, I don't have a theorem because in a sense, the other class of solution to look at would be wormholes, which are much more complicated to handle because you have a topology change there, and it's much more complicated to predict the stability of wormholes.
Anyway, in the end, it wouldn't be nice to live in one of those bubbles. It wouldn't be.
But you see also here, when you have a wormhole, when you're close to do the chronological horizon, you have all this accumulation, these light rays. You can imagine that cut at a constant time of the left mouth here. Here, if I cut, there is one ray. Here, if I cut, there are two rays. Here, if I cut, there are three rays. And then if I cut close here, there are infinite rays. So each ray has an energy. And so the energy is blowing up also there. The problem is that to be predictive, here you need to have a quantum gravity, and that we don't have yet. So, for example, I think that it would be very useful to use quantum gravity models that we have nowadays and interpret what happens close to the formation of a chronological horizon from the microscopic point of view. I'm pretty sure something goes wrong in the fundamental theory. Something forbidden is up to the fundamental theory. The fundamental theory will say, you cannot do that. And that would be the proof that basically you must have this global hyperbolic space-time. But why they are global hyperbolic in the first place?
Yeah.
Why we are not living in the diamond and we live in graphite? And I think that has to do with the way the emergence happens. The condition under, and it may be that it's not something you can predict just having the equation for the fundamental system. You need to have the initial condition also there. Physics is not just equation, it's what you put in the equation and then you spit out an answer. So, you know, take carbon again, you can have diamond or you can have graphite. And it's not that the carbons are different in the two cases. The atoms have the same, the same valences, the same links. But the condition under which you develop the condensation to a large scale structure are completely different, and that makes it different.
Yes, absolutely. And I know that both you and also people working in group field theory, I mean, there is growing interest in the results of condensed matter physics, of course, because studying condensed matter, we can, in a sense, better grasp or try to better grasp what could have had happen or could happen at a more fundamental level, even if we do that by analogical reasoning, basically. Anyway, I don't know whether other people do have questions or other remarks. No? Okay. So
Can I
our speaker again. Ah, sorry.
Sorry. Can I ask one? Maybe he wants to go away though. He said he had some.
Well, if it's a very brief, yes, why not? I mean.
Okay. So first of all, in this scheme you are showing now, this only applies to wormholes, right? If your superluminal travel comes from the Alcubierre drive, this.
No, there is the same issue. There is the same issue. This is just an example. Every time you are close to have the first light rays that can close in a loop, then that light ray basically draws the chronological horizon. You always have a chronological horizon.
I understand
you didn't have it
but in this case, in this case, maybe I'm misunderstanding something, but you don't have a loop because you have to carry this bubble in order to close the loop. So the light rays cannot follow the whole loop, right?
Yeah, but once you follow a loop, I mean, it's more difficult to visualize, but basically when you do this kind of things,
okay, but it's still the same.
You see, the problem you see what it is that if you start depicting the things already done, like with the two, imagine the two wormhole can be the travel of the spaceship. The problem is that you have to think of it dynamically. Initially, there is a completely sane universe where there are no closed time-like curves. Now you take something that can travel faster than light. So it's like basically going back to this picture and doing this, going from 0 to 1 to A2, and then to close the loop, you have to wait, standing still. From A2, you go back to A0, and then you close the loop.
Sure.
And the problem is that the first time you do it, if before space-time it didn't have this closed loop, there will always be a boundary between the region in which the loops start to happen and where they weren't. And this boundary is always a chronological horizon. It's basically something that has to do with...
Yes. I understand what you're saying. I don't see it, but I think that...
I agree with you that it's much more difficult to visualize in this case, of course.
Right. Yeah, but I see. Thanks. And also, why are you saying that the Gödel universe is garbage in and garbage out?
I don't say that. That is... No, it's that people sometimes say, it's garbage in because you're putting a global rotation. So the problem is that you're putting something exterior that is global. It's not a local notion. And that is basically a bit cheating the rules of GR, because on the other side, you see, of course, I can take Minkowski, identify time, and make a loop in time. I mean, I change the topology from R1 times R3 to S1 times R3, and then I'm done. I have closed time-like curves. So the problem is that people say, okay, if you put initial condition with a global rotation, of course, but who selects this axis of rotation? There is nothing exterior to the universe. It's not that there is someone taking these things and putting in rotation. So from this point, it enters again into those solutions which are considered unphysical from the start and from the boundary condition you put them to determine the solution. By the way, this solution is also a counterexample to the Mach principle because it has the same content locally of dust and cosmological constant as Einstein's static universe, but has a completely different causal structure. If the geodesics are different, so it tells you that the local notion of what is inertial is not determined just by the distribution of energy from the energy matter content.
I think Gödel derived it in order to get a counterexample, right? Maybe.
But actually, there are different stories. There is a book I read where they were saying that actually Gödel had an argument about the fact that Einstein said that there was no preferred time in general relativity and that there was probably a block universe as an interpretation.
Right.
But Gödel instead say, no, there is not even a well-ordered notion of time. So apparently, initially, it wasn't to attack, he didn't do it to attack the Mach principle, was more doing it to attack the fact that there was even a notion of time. He wanted to kill time.
Fascinating. Yeah.
Okay.
Nice.
Thank you very much. Thank you, Lorenzo. Thank you all who took part in the seminar today, and especially to Stefano Liberati. And I must confess it was one of the most, even funny talks that we had in our whole series. It was very interesting. Thank you very much, Stefano.
Thank you. Thank you for the invitation.
Okay.
Bye, everybody.